Oh, good morning again. This is Linear Algebra, Math 313, Lecture 1. And linear algebra starts with the problem of solving linear equations. So let me just write that down. Linear algebra starts with solving linear equations. Either one equation or a system of equations. So you should have done this in algebra in high school, things like solving two equations and two unknowns. But we're going to generally have more than two variables, more than two unknowns. And we're going to start today with one equation. So it can be very simple. Solve the equation 2x equals minus 9. So this is a linear equation in one variable. Or maybe 4x plus 7y equals 5. So this is one linear equation in two variables. And the general form of one linear equation in n variables is a1x1 plus a2x2 plus a3x3. Maybe we have n variables, a(n)xn equals b. So this is what one linear equation in n variables looks like. A1, A2 up to AN, these are the coefficients, and B, this number on the right-hand side, these are numbers which in linear algebra are called scalars. So for some reason, in linear algebra, scalar means a number. So I'll often usually call these things scalars instead of numbers. And this equation is said to be homogeneous if the right-hand side number is 0 and the equation is not homogeneous or inhomogeneous if the right-hand side is different from 0. So, and they're slightly different results associated with homogeneous and inhomogeneous equations. Also, it doesn't matter what letters we use for the variables. We could write x1, x2, or we could write them variables as y1, y2, or z1, z2, or x and y. Or if we had three variables, we could call them x1, x2, x3, or x, y, z. It makes absolutely no difference. It's our choice what letters to use for the variables. If you have more than three variables, we almost always use one letter with subscripts. If you have one or two or three variables, you could use letters with subscripts. You could use x or xy or xyz or uvw. It's really of zero importance what letters you choose. Especially when we're writing equations in n variables, we use what is called sigma notation a lot. Sigma notation. You've seen this in calculus. This is the capital Greek letter sigma. And if you write sigma, let's say J goes from R to S, A sub J, this means you sum this quantity A sub J from R to S. AR plus 1, AR plus 2, up to AR plus, up to A sub S. And
That's the same as the 20%.
Is there a question about this? And this only makes sense if R is less than or equal to S. And if R were greater than S, then this sum, there's nothing to sum, so we would say the sum is 0. So for example, you have summation, j goes from 3 to 7, j squared. This means 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared, which if you add it up is 9 and 16 is 25, plus 25 is 50, plus 36 is 86, plus 49 is 135. Right? So this is just sigma notation, which you have to be familiar with because you use it in calculus when you're doing integration, certainly. So you can also write the linear equation using sigma notation. The summation I goes from 1 to n, ai xi equals b. This is just another way of writing a1 x1 plus a2 x2 all the way up to an xn equals b. So this is our equation. This is called the zero equation. If all the coefficients ai are 0, ay equals 0 for all I from 1 up to n, then the equation is just 0 times x1 plus 0 times x2 up to 0 times xn equals b. And then it's clear that the zero equation has no solution if b is different from 0, because no matter what you choose for the values of the variables x1 up to xn, you're going to get 0 on the left-hand side. So you'll never get something non-zero. It will never be equal to b. But everything is a solution if b is 0. And the form in which we write solutions is very important. So a solution of the equation a1 x1 up to an xn equals b is a sequence of numbers, a sequence of scalars, x1 up to xn, that solve the equation. You plug in these numbers and you get b. And we write the solution as a vertical n-tuple. What that means is x1, x2 down to xn is the solution of the equation. So we say that, and we call this an n-dimensional vector. Or just a vector, or n-dimensional column vector, or simply a vector when it's clear what the number of scalars is.
Hey, excuse me.
Yeah.
Can you rewrite that? I can't understand the writing. The vertical n-tuple.
Vertical n-tuple, yes. Sorry, my writing is my writing, but there will be notes that are printed out that'll be on Blackboard very soon, where everything is legible.
Okay, that's fine.
Yeah. So this vertical n-tuple is an n-dimensional vector, column vector. And the scalars, x1 up to xn, are called the coordinates. For this x of the vector x. So when you have to write down the solutions of a linear equation, you write the solutions as vectors. So let's take I don't know, an example. If you have the equation 4x plus 7y equal 5, there are a lot of solutions. The vector 3 minus 1 is a solution because 4 times 3 plus 7 times minus 1 is 12 minus 7. That's equal to 5. So this vector is the solution of this equation. So we think of linear equations as having solutions that are vectors. And everything in this course involves vectors. So this is also a class where we not only solve equations, solve problems, compute matrices, and so forth pretty soon. We actually have to prove things because it's a mathematics class. It's not just a techniques class. In terms of techniques, we'll be using Maple for a lot of problems, but we have to understand the notion of proof. And it starts with the world's simplest result, which is lemma 1.1. It's lemma 1 in chapter 1 in the notes. Every non-zero linear equation has a solution. Remember, what is a linear equation? A1 x1 plus A2 x2 up to A sub n x sub n equals 0. Non-zero means, let me start to write proof here because the proof, there'll be more to this lemma. Non-zero means some coefficient is different from 0. It means that A sub, let's say J naught, is non-zero for some J naught in the set of numbers from 1 up to n. So if we're looking at this equation, let's see, write it like this. I have A1 x1. I have A sub J naught minus 1 x J naught minus 1. A sub J naught x sub J naught. A sub J naught plus 1 x sub J naught plus 1 up to A n x n equals 0. And if the equation is non-zero, some coefficient is non-zero. Maybe many of them or all of them are, but at least one is. So let's say that A sub J naught is different from 0. So I claim this equation always has a solution. And how can you get a solution? Well, if U equals B. If you rewrite this equation, or not even rewrite this equation, here's a simple solution. Let A sub j, that x sub j, the variable xj, set it equal to 0 for all j different from j naught, and let x sub j naught be equal to b divided by a sub j naught. So this is permissible because you're dividing by a non-zero scalar. So why is this? So I claim that this vector with all zeros, except at the j naught coordinate, this is b over a j naught, and then all zeros. I claim this vector is a solution. Why is that? Because you're letting all the x's be equal to 0 except this guy. So when you plug in 0 for all these x's, that all disappears. And x sub j naught is b over a sub j naught. The aj naughts cancel, and you get b. So this is a solution. All right? So we win. This is a solution. Every non-zero equation has a solution. Now, if there's only one variable, if n is equal to 1, this equation is just a1 x1 equals b. It's non-zero, so a1 is different from 0, and the unique solution is b over a1. So if n equals a1, this is the unique solution. It's a one-dimensional vector. If n is at least 2, then choose any scalars for the variable x sub j for all the j different from j naught. And then I claim we can get a solution by picking the right value for the variable x sub j naught. Namely, do what you learned in high school algebra. You have, let me write it out here. Remember, our equation looks like a1 x1 up to a sub j naught minus 1 xj naught minus 1 plus aj naught xj naught plus aj naught plus 1 xj naught plus 1 up to an xn equals b. So hold this fixed and put everything else on the other side of the equation. aj naught xj naught equals b minus a1 x1 up to a j naught minus 1 xj naught minus 1. I subtracted this, and I also subtract this, aj naught plus 1 xj naught plus 1 up to an xn. So we want xj naught to satisfy this equation. So simply divide everything by aj naught, and this is what xj naught has to be. So for any choice whatsoever of the scalars, x1 up to xn except xj naught, you can always find xj naught, and here's a formula for it that solves the equation. So back in my lemma, this was the lemma, every non-zero linear equation has a solution. Solution is unique if there's only one variable, but if there are two or more variables, there are infinitely many different solutions. There's a whole, because you can choose these variables, these coordinates in any way you like. So a non-zero linear equation in two or more variables always has infinitely many solutions. And we want to look at all of solutions, the set of all solutions. So what is called the solution space of a linear equation is the set of all solutions or all vectors that solve the equation. If you have the zero equation, there's a solution if and only if the equation is homogeneous. Let's go back to look at the equation in two variables. 4x plus 7y equals 5. We're going to find all solutions. So we could do the following. 7y is 5 minus 4x. So y is 5 minus 4x over 7. So you can choose any value for the coordinate x, and then y has to be this. So the vector xy is a solution if and only if y is 5 minus 4x over 7. So what is the solution space? It's the set of all vectors x and the second coordinate 5 minus 4x over 7 for any value of x. If we're looking at just real numbers, for any x in R. This means the real numbers. And this is just the way you write in mathematics. X is a member of the set of real numbers. So the solution space is all vectors that look like that and nothing else. That's exactly the solution space. Suppose we take an equation in 3 variables. 3x minus 2y minus 5z equals 17. I can go about finding the solution space by solving for any of the variables. Suppose I want to solve for the variable z. So 5z is 3x minus 2y. Sorry, that's not right. Yeah, sorry, that is right. 5z is 3x minus 2y minus 17. Let me write it like this, though. 5z is minus 17 plus 3x minus 2y. So z is minus 17 plus 3x minus 2y over 5. So a vector x, y, z is a solution if and only if z is equal to this function of x and y. So I take the vector x, y, and the third coordinate is minus 17 plus 3x minus 2y over 5. That's a three-dimensional vector. And I look at the set of all such vectors where x and y run through the set of all real numbers. Let's see. What's a particular solution of this equation? A particular solution is x, y, z equals, suppose I take x equal to 3, I take y equal to 6, and what is z? Z is minus 17 plus 3 times 3 minus 2 times 6 over 5. That's the vector 3, 6, minus 17 plus 9 is minus 8. Minus 8 minus 12 is minus 20. Minus 20 over 5 is minus 4. So one particular solution of this equation is 3, 6 minus 4. You plug it in and you see that it works. 9 minus 12 is minus 3 plus 20. 20 minus 3 is 17. So this is the solution space for this equation. Now, I've been solving these equations in real numbers, but in linear algebra, we use real numbers, and we also need to be able to use complex numbers. So you might have an equation like, so linear equations in complex numbers. So we write the set of complex numbers as this by C. And suppose we have an equation like 1 plus I times Z equals 2. We want to solve that equation. So Z is 2 over 1 plus I. And we usually try to get the i's out of denominators. This is 2 over 1 plus I. And we can multiply that by the complex conjugate of this, 1 minus I over 1 minus I. So this is 2 minus 2I. And this is 1 plus 1 over 2. This is 1 minus I. So the solution of this equation is the complex number 1 minus I. We're not going to do very much using complex numbers in this course, but by the time you reach a 300 level math class, you should be familiar with the complex numbers and know how to add, subtract, multiply, and divide them. Any questions so far? Okay, now, so what I just covered was section 1.1 in what will be the notes that get posted. 1.2, I'm just going to spend a little bit of time talking about vectors. And right now for us, vectors are n-dimensional column vectors. So we usually write by Rn is the set of all n-dimensional column vectors. So R2 is the set of all two-dimensional vectors. You can write this as a set of all vectors x, y, where x and y are real. Or you can write this as a set of vectors x1, x2, where x1 and x2 are real scalars. Doesn't matter what letters you use for the coordinates. And in general, suppose we have a vector x in Rn, n-dimensional, and y, an n-dimensional column vector in Rn. So we say x equals y. These two vectors are equal if and only if they are equal coordinate-wise. x1 equals y1, x2 equals y2, x3 equal y3, all the way down to xn equal yn. Right, so two vectors are equal only when each of their coordinates is the same as the corresponding coordinate in the other vector. Right? And what is called the zero vector is just the vector 0 with all coordinates equal to 0. That's the n-dimensional 0 vector. So there's some elementary algebra or arithmetic, if you like, for vectors. We can add vectors in the same dimension. So if x is the vector x1, x2 down to xn in Rn, and y is the vector y1, y2 down to yn in Rn, we can define x plus y, that's x1, x2 down to xn, plus y1, y2 down to yn, by adding coordinate-wise, x1 plus y1, x2 plus y2, down to xn plus yn. This is vector addition. And you can subtract the vectors just by subtracting the coordinates. And there's also an operation called scalar multiplication. You can multiply a vector by a scalar. A scalar is a number. So if you have a number, a scalar c, you can take the vector x1, x2 up to xn, so c times x. You just multiply every coordinate by c, cx1, cx2, down to cxn. This is scalar multiplication. So just to make a very concrete example, if I have the vector 1, 2, 3, and the vector 4, 5, 6, I add them by adding coordinates 5, 7, 9. And I subtract them. I get -3, -3, -3. And if I take the vector 1, 2, 3, and I multiply it by the scalar 7, I multiply each coordinate by 7. 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21. Okay. Any questions about this? This is just the elementary arithmetic of vectors. And vector addition and scalar multiplication satisfy all the nice properties you expect in arithmetic. So for example, so notice you can add and subtract vectors of the same dimension. So if you take the vector 1, 2 and the vector 3, 4, 5, you try to add these two vectors, this is not defined, not possible. You cannot add a two-dimensional vector and a three-dimensional vector. You can only add vectors of the same dimension. But if you have vectors x, y, and z, let's say they're all n-dimensional vectors, vector addition is a binary operation. You add two at a time. You have x plus y, that's a vector, and then you can add z to that. Or you could take x and add it to y plus z. And if you do x plus y plus z or x plus y plus z, you always get the same vector. So this is, in the way you describe this property of vector addition, is you say that it's associative. It's also the case that x plus y equals y plus x. That means vector addition is what we call commutative. There's also the zero vector. If you add the zero vector to any vector x, you just get back x. I mean, that's clear because if you take x1, x2 down to xn and add the vector, which is all zeros, you're just adding 0 to each coordinate. So you don't change any of the coordinates. And if you define see, -1, that's a scalar times x, is just the vector you get by multiplying every coordinate by x. We just call that minus x. And x plus the vector minus x is the zero vector, because you have x1, x2 down to xn, and you're adding minus x1 minus x2 down to minus xn. And when you add, you get x1 minus x1, x2 minus x2, down to xn minus xn. These are all zeros. So x plus minus x is 0. If you've taken algebra, well, you probably haven't because this is a prerequisite, but in algebra, you would say that vectors form an additive abelian group. You can add them and subtract them, they behave nicely. Scalar multiplication also has very nice properties. First of all, so this is properties of scalar multiplication. Multiply any vector by 1, you're just multiplying every coordinate by 1, so nothing changes. If you take two scalars, c and c prime, and multiply them together, and multiply the vector x by c prime, that's exactly the same as if you took the vector x, multiplied it by c prime, and took that vector and multiplied it by c. And they're kind of distributive laws for scalar multiplication. C plus c prime times x is cx plus c prime x, and c times x plus x prime is cx plus cx prime. So all the nice things you do normally in arithmetic, you can do with vectors and vector addition and scalar multiplication. All right. So vector addition, the way it's defined, is a binary operation. You can add two vectors. But once you can add two, you can add three. You just add two and then add the third one to it. And more generally, if x1, x2, x3, up to xn are vectors in the same dimension, and c1, c2, up to cn are scalars, I could take the vector x1 and multiply it by the scalar c1. I can take the vector x2 and multiply it by the scalar c2. I can take the vector x3 and multiply it by the scalar c3. I do that to each of these vectors. When I get up to the vector xn, I multiply it by the scalar cn. So now I have n vectors, and I can add these. So I have this new vector. Everything's in Rn. And this is called a linear combination of the vectors x1 up to xn. Actually, this n is different. Maybe I should, this is in some rk. And it's not the dimension of the vector here. I simply have, so a linear combination of vectors is a vector which you get by multiplying each vector by a scalar and adding them all up. So this is what is called a linear combination. And this is very, 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 very important and used constantly in linear algebra. Let me do an example. Suppose I take x is the vector 1, 2, 3. Suppose y is the vector 3, 4, 5, 6. Suppose z is the vector 7, 8, 9. And I want to compute 5x minus 3y plus 2z. So what is that? That's 5 times the vector x, which is 1, 2, 3, minus 3 times the vector y, which is 4, 5, 6, plus 2 times the vector z, which is 7, 8, 9. 5 times this vector is 5, 10, 15. 3 times this vector is 12, 15, 18. 2 times this vector is 14, 16, 18. What do I get? I get 5 minus 12 plus 14, 10 minus 15 plus 16, 15 minus 18 plus 18. So this is 5 plus 2, 7. This is 10 plus 1. This is 11. And this is 15. So if I did my arithmetic correctly, this linear combination is equal to the vector 7, 11, 15. Here, take a piece of paper and compute the following. Suppose I take, you compute this, 3 times 2 minus 1 plus 8 times minus 4, 5. Spend a second and compute this vector. What is this linear combination? Someone get an answer? Someone tell me what vector that is? What is it? Let's see. 3 times 2 minus 1, that's 6 minus 3. 8 times this vector is minus 32, 40.
Is it negative 26 and then 37?
So this is negative 26, 37, right? Exactly. That's this linear combination of these two vectors. Remember when we solved the equation 4x plus 7y equals 5, the solution was all vectors x, y, where x could be any scalar, and y was 5 minus 4x over 7. So I can write this in a somewhat nicer way, I think. This is x, and the second coordinate is 5/7 minus 4/7 x. I can write x if I like. I can think of it this way. You never really write this down. 0 plus x. So this is the sum of two vectors. The constant vector 0, 5/7 plus the vector x and minus 4/7 x. And x is a scalar. I could factor it out of this vector. This is the vector 0, 5/7 plus x times the vector 1 minus 4/7. So if I start with this linear equation, the solution space is all vectors that look like this. It's this fixed vector, which is a particular solution of this equation. If I let x equal 0, I get y is equal to 5/7, plus any scalar multiple of this vector. So this is just another and somewhat more informative way to write the solution space of this equation. Another equation we looked at earlier was 3x minus 2y plus minus 5z equals 17. And we saw the solution space was all vectors x, y, z that really look like x, y, and z was minus 17 plus 3x minus 2y over 5, which I could write like this, x, y, minus 17 over 5 plus 3/5 x minus 2/5 y. And I sort of think of this as I'm sort of like lining these things up in columns. It's like you have zeros here and zeros here. And if I do it like that, then I can write this as the sum of three vectors. 0, 0, minus 17 over 5. Plus this vector x0, 3/5 x, plus the vector 0, y, minus 2/5 y. And I can factor an x from here and a y from here. So every solution is of the form 0, 0, minus 17 over 5, plus x times the vector 1, 0, 3/5, plus y times the vector 0, 1, minus 2/5. So this is a more elegant way, and we'll see soon, a much more informative way to write the solution space of this linear equation. It's this fixed vector, which is a particular solution of the equation, plus all scalar multiples of this vector and this vector. And these are each solutions of the corresponding homogeneous equation. If you replace the 17 by a 0, these will be solutions of the homogeneous equation. But we get this form of the solution just by using the elementary arithmetic of vectors. Okay, so I'm going to say a little bit more about vectors in Rn. So Rn, which is the set of all n-dimensional column vectors with real coordinates, is an example of what is called a vector space. There are other vector spaces, but this is by far the most important and the one we spend most of our time studying in this course. So you should be familiar with the language of sets and subsets. So let W be a subset of Rn. So the notation is simply W, this means is a subset of or is contained in Rn. We say that, so this is sort of terminology. W is closed under vector addition if for all vectors x and y in W, we have x plus y is in W. That is, if you take any two vectors in W and add them, you still stay inside of W. You can think of it like this. Here's Rn, and sitting inside Rn is this subset W. And if you take any two vectors, x and y in W, the sum is also in W. So adding two vectors doesn't take you outside of the subset. And we say W is closed under scalar multiplication if for all scalars C and all vectors X in W, we have C times X is still in W. So if you take a vector in X and you multiply it by any scalar, positive, negative, or zero, it stays inside W. And what is extremely important in linear algebra are subspaces of vector spaces. So a subspace of Rn is a subset of Rn that is, well, that satisfies three properties. First, the zero vector, 0, a subspace is a subset W. 0 is in W. W is closed under vector addition. And W is also closed under scalar multiplication. So if you have a subset of a vector space, a subset of Rn, which contains the zero vector and is closed under addition, vector addition, and scalar multiplication, then it's what's called a subspace. And so we have sort of like trivial examples of subspaces of Rn. The first is Rn. It's a subspace of Rn, because every set's a subset of itself, and Rn is closed under vector addition and scalar multiplication. And 2, W just consisting of the zero vector. This is sort of like the zero subspace. Of course, the zero subspace contains 0 and is closed under vector addition. 0 plus 0 is 0. And it's closed under scalar multiplication. Any scalar times the zero vector is just the zero vector. So these are sort of the trivial examples. And it's the non-zero example, non-trivial examples that are really the most interesting thing. Also, I should add that if W is a subspace, then W is not only closed under vector addition and scalar multiplication, W is closed under taking linear combinations of vectors. So, why is it that we like subspaces so much? Get to what is the most important little theorem I want to prove right now. So this is a theorem. This is in the notes. You haven't gotten notes yet, but you will shortly. Theorem 1.2. The set W of solutions of the homogeneous linear equation in n variables, a1x1 plus a2x2 up to an xn equals 0 is always a subspace of Rn. Okay. Proof. Consider the 0 vector. If I let all the coordinates be 0, or the x's be 0, I get a1 times 0 plus a2 times 0 plus an times 0 is certainly 0. So the 0 vector is in the solution space. Suppose I take two vectors, x with coordinates x1 down to xn, and y with coordinates y1 and yn, be in the solution space. So what does that mean? They both solve this homogeneous equation. So a1x1 plus a2x2 up to an xn is 0. And a1y1 plus a2y2 plus an is 0. Suppose I add these equations. I get a1 x1 plus y1 plus a2 x2 plus y2 up to an xn plus yn equals 0. But what is the vector x plus y? It is coordinates x1 plus y1, x2 plus y2 down to xn plus yn. And that's the solution of this equation. So if x and y are solutions, x plus y is the solution. So the solution space of a homogeneous equation is a subspace. And again, if I take this equation and I multiply it by c, or if I multiply each of the x's by c, see what is c times x? Cx is the vector cx1, cx2 down to cxn. What do I get if I plug this into the equation? I get a1 c1x1 a1 cx1 plus a2 cx2 a3 cx3 up to an cxn. But I can factor a c out. This is c times a1x1 a2x2 up to an xn. But this is 0. This is c times 0, which is 0. So this vector is also a solution. So cx is in W. So the set of solutions to a homogeneous equation is a subspace. Okay. That is really, really important. Let's look at an example. Suppose I take the equation 4x plus 5y equals 0, and suppose I let W be the solution space. So we solved this already. Y see? So if you have a solution of this equation, 5y is minus 4x, y is minus 4/5 x. So any vector xy that's a solution is x minus 4/5 x, or x times 1 minus 4/5. So the solution space is just all scalar multiples of the vector 1 minus 4/5. And this is a subspace. If I take the vector x plus 2y plus 3z equals 0, for any solution, so I'm going to compute the subspace of solutions. This is a homogeneous equation in 3 variables. Simplest thing is to say x is minus 2y minus 3z. So any solution x, y, z looks like minus 2y minus 3z, y, z. I can write this as the sum of the two vectors minus 2y, y, 0, and minus 3z, 0, z. Right? Here I put all the y's in one vector, all the z's in one vector, and check, you add, this is what you get. And this is y times the vector minus 2, 1, 0. And this is z times the vector minus 3, 0, 1. So the solution subspace is the subspace. It's all these linear combinations, minus 2, 1, 0, plus z minus 3, 0, 1, for any values of y and z. Right? Okay, well, are there any questions? Because I think I've done a lot so far. In fact, I think I've done as much as I want to do today. I will upload the notes sometime today to Blackboard, and let me just pause the recording.